Okay, so welcome back to this next video in which we are discussing Cosets and Lagrange's theorem. Okay, so the first thing we're going to do in this video is we're going to do an example. Okay, so it's always good to have a concrete example rather than just keeping it arbitrarily general. Okay, right, so our large group in this example, capital G, is going to be the group of integers under addition. Okay, so the set of all integers with that single composition law defined on them, which is addition. Now, of course, we know that the integers can have more than just the addition composition law defined on them, but forget all of that, forget multiplication basically. Just think about addition for the basis of this. Okay, right, so we've got this group, which is the set of all integers with addition defined on it. Okay, so now what we need is a subgroup for which we're going to take the cosets of it. Okay, and our subgroup is just going to be the subgroup 5z. So it's going to be all integer multiples of 5. So remember back to the video on subgroups where we studied the subgroups of the group of integers under addition. We saw that all things of the form nz, where n was some natural number or 0, so 0, 1, 2, 3, 4, 5, etc. All of those were subgroups of the group of integers under addition. Okay, so what does this actually mean? This means all integer multiples of 5, basically. So it means 5 times z. Now, I know I said forget about times being defined here, okay, but for the basis of defining what this set is, remember multiplication for now. Okay, so you take all of the integers and you multiply them all by 5, basically. So this is all integer multiples of the integer 5. Okay, and that creates you a subset of the group of integers. And in fact it is actually a subgroup, so it's closed under composition, so if you add any two multiples of 5 together you'll get another multiple of 5. And to make this more concrete I might just actually write down what this set will actually look like. Okay, so if we think about going through all of the integers, so we'll start with 0. When we multiply 5 by 0, of course we end up with 0. Then we'll have 1. When we multiply 5 by 1 we'll end up with 5. Then we'll have negative 1. When we multiply 5 by negative 1, we'll get negative 5. Then we'll have 10, which will be 5 times 2. Okay. Then we'll have negative 10, which will be 5 times negative 2, and it will go on. So you'll have 15, negative 15, etc. ... Okay, so that is what this set will look like. It's all the integer multiples of 5. Now, this is closed under composition, so whenever you add two of these together, you get another integer multiple of 5. Okay, we have the identity element here, 0, which will add to any other element of this subset to give that other element back again. We know it will bear associativity because it inherits that from the larger group. And finally, we have inverses in here, so for 5 we have negative 5, for 10 we have negative 10, 15 we have negative 15, etc. Okay, right, so here is our subgroup of the group of integers under addition. Okay, so what we now want to do then is construct some cosets. Okay, now in the case of this example, we don't need to worry about left and right cosets because our larger group here is an abelian group, it's commutative. So in fact, the left coset of capital H under any element little a will actually equal the right coset of H under the element little a. So I can just say the coset, but for the basis of writing something down, I will write it as though it is the left coset, simply because left cosets, the notation looks more natural somehow. Okay, right, so let's quite simply use as our little element a, let's use the element 1. Now 1 is an element of the larger group, but it's not an element of this subgroup, it's not in the integer multiples of 5. Okay, so I've taken an element that's in the larger group but isn't in the subgroup, and now what we're going to do is generate the left coset of H under little a. And sometimes people would write this 1 plus capital H, or even 1 plus 5z if you wanted to actually substitute in for capital H 5z, okay, because here our composition is actually called addition, okay, and when your composition is called addition, often it's more conventional to actually put in add, because when you have it like this, it looks as though it's multiplication. Okay, now of course addition is a composition, but it's just common notation to write it as like this, rather than writing 1 capital H, okay, because that, you know, kind of implies multiplication. Now, of course, addition is a composition rule, multiplication is a composition rule. In that respect, they're the same, but this, for old classical reasons, we do it like this. Okay, right. Let's actually construct this coset then. So we want to take all of the elements in this subgroup of 5z here, and we want to compose them with 1 on the left, basically. We want to add 1 to them all, basically. Okay, so let's go through and do this. So 0, what will happen to that? It will become 1. 5, what will happen to that? It will go up to 6. Negative 5 will go up to negative 4. Okay, 10 will go up to 11. Negative 10 will go up to negative 9. 15 will go up to 16. Negative 15 will go up to negative 14. So everything on the number line is being shifted 1 to the right, basically. So if I draw out the number line here, so here will be 0, here will be 5, here negative 5, here negative 10, here 10, and basically everything is just going to be shifted 1 to the right, basically, up by 1, okay? And that's going to then create us the left coset of 5z under the element 1, basically. Or you could just say the coset of 5z under 1, because of course the left and right cosets are the same. Okay, so now that we've seen an example then of a coset, what I now want to turn our attention to is Lagrange's theorem. Now the way that we're going to approach Lagrange's theorem is as a derivation rather than as a proof. Okay, so Lagrange's theorem is a theorem from finite group theory. Okay, what we are going to do firstly is we're going to study how we can use cosets to partition up a group, basically, and this we will see is something that is applicable to infinite group theory as well. It's not something that's just applicable to finite group theory. However, when you apply this partitioning of a group up into the cosets to finite group theory, Lagrange's theorem then becomes a very natural result from that. Okay, so that's the way I'd rather approach Lagrange's theorem, rather than as a statement of it and then a proof. So I'm not initially going to state Lagrange's theorem. Initially, what we're going to study instead is how we can partition up the group using cosets. Okay, right, so let's turn our attention to that now. Okay, so hopefully you're familiar from set theory with the concept of a partition, basically. So quite simply, if you have a set, what a partition is a way of dividing that set up into a bunch of subsets that when unioned together make the entire set, and which have empty intersections, basically. So quite simply, you can draw a picture of it. So if you've got a set here, okay, then a partition of that set is quite simply a way of splitting it up. Okay, so dividing it up into subsets. Okay, so here we've got 5 subsets now. I'll colour them in separate colours. So here we've got one subset in orange, then we'll have subset in red here, second subset, the third subset we'll have in turquoise here, okay, the fourth subset we'll have in blue here, whoops, and then the fifth and final subset we'll have in pink here. Okay, so the absolutely formal definition of a partition of a set is that a partition itself is a set. Okay, so we can call it P, and this set is going to consist of subsets of our original set. So we'll call our original set over here S. So S is the entire thing here. I'll colour it in yellow or outline it in yellow. So the entire set here, consisting of these 5 subsets, is the set S. So our partition of the set S is a set containing these 5 subsets which we've split the large set S into. Okay, so we'll have subset orange here. Okay, and I'll colour code it. So here we have subset orange inside of set P. Then we'll have subset red, which can be represented here, subset turquoise, which can be represented here, subset blue, which can be represented here, and subset pink, which can be represented here. Okay, like so. So I'll colour them all in. So this one is subset red, here we have subset turquoise, here we have subset blue, and here we have subset pink. So that's the absolutely formal definition of a partition, that it is a set consisting of subsets of our original set S, and together, if you union all of these subsets inside the partition, together you get the entire of S back again. So together they cover all of S, and they all have empty intersections. So if you intersect any of these two subsets together, you end up with the empty set, basically. So there are no, well, every element of the set capital S is in one and only one of these subsets, okay? They don't overlap at all, okay? That's what is meant by them having empty intersections. Okay, so that's the absolutely formal definition of what a partition of a set is. We're not really going to need the absolutely formal definition. We just need the intuitive definition that what you're doing is dividing the set up into pieces. That's the concept of a partition. Okay, so it's a very sensible name. Right, so what I claim is that we can use cosets to divide up the set that underlies the group. So let's now draw another picture here. So once again, we'll have a box here, and now this box represents the entire group. So this represents the set of all the symbols in the group, basically, the set that underlies the group. So here's my large group, capital G, and I'll color code this in purple here. Okay, and now what I'm going to do is I'm going to find some subgroup of capital G, okay, which I'll mark on here. So we'll have our subgroup of capital G, and we'll once again call that capital H, and we'll colour capital H as we always have done in red here. So here's capital H. And now my claim is that what we can do is we can take cosets of this subgroup, capital H, and we can use this to partition up the set just like this, basically. Okay? And you can either do this with left cosets or you can do this with right cosets. Of course, if the subgroup is a normal subgroup, then those will be the same way. They'll be the same thing. So that means that there's only one way of partitioning the group capital G up with that subgroup. If it's not a normal subgroup, then those cosets will not necessarily be the same, okay, and therefore you'll end up with two different ways of partitioning up the set. So if you do it with left cosets, you'll end up with a different way to if you do it with right cosets. Okay, right, so let's explore this in a bit more detail. So, how do we do this then? How do we go about this? At the moment, we've just got our subgroup, capital H, which we know is a subset of capital G. So, quite simply, either the subgroup capital H is the entire group, and we know, of course, that is one of the trivial subgroups, so it is plausible that capital H could be the entire group. And if capital H is the entire group, then there is absolutely no element of capital G that is outside of capital H. So this great big space here would have nothing in it, basically. Okay? In that case, that's your partition. Capital H is the only subset that you'd have in your partition. Okay, that's quite a boring example. If it's not the case that capital H is the entire group, then there will be an element that is in capital G that is outside of capital H. Okay, and we will call this little element little a. Okay, so little a is just an element that's in capital G but is not in capital H, basically. It's not in the subgroup capital H. What we can now do is construct either the left or right coset of capital H under A. Now I will go with the left coset, but you could do it with the right coset. Okay, and note, if it's not a normal subgroup, those will be different. Okay? Right, so we now construct the left coset of H under A, and we have already shown that that left coset of H under A will be completely distinct from the subgroup capital H, we've shown that there cannot possibly be an element that is in both of these, basically. Okay, so all the elements in here are distinct from the elements in here. So these two truly are non-intersecting, basically. They do not overlap. Okay, right, so we've got our first coset, basically. Now what we do is we continue our argument on again. Okay, we say, okay, either these two together now unioned make the entire group. Okay, so this subgroup here unioned with this coset, either they make the entire group and there's nothing outside of them, or again there is another element that is outside of them, some little b here, let's say. Okay, and now what we're going to do is we're going to create the left coset of capital H under little b here. Okay, so I'll mark this on. Now my claim is that this is distinct not only from the subgroup capital H, but also from the other coset that we had here, which was the left coset of H under A. Now, what we know is that this left coset of H under this element little b has to be completely distinct from the subgroup capital H itself. Okay, and we know that because by assumption little b was not in the subgroup capital H. Remember, we assumed that little b was outside of the subgroup capital H and also, in fact, the left coset of H under A. Okay, so that certainly means it's outside of the subgroup capital H. And we know that whenever we take the left coset of a subgroup capital H under an element that is not in that subgroup, you end up with a set that is completely distinct from the subgroup. So we know that our left coset of H under B is completely distinct from the subgroup. What we haven't yet made crystal clear is that it will also be distinct from this left coset of H under A. Okay, so all we've got to prove that is that we assumed little b was outside of the left coset of H under A. Okay, and what we now need to prove is that its entire left coset, the left coset of H under B, is also completely distinct from that left coset of H under A. Okay, so quite simply, we're going to do this by contradiction. Okay, we're going to do a proof by contradiction. So we're going to assume the opposite. We're going to assume that we have some element in the left coset of H under B, okay, which will be some element of the form B composed with a little h, where little h is some element of the subgroup, because that's the general form of something in this left coset of H under B. Okay, and we're going to assume that it is actually equal to an element in this left coset of H under A. Okay, so we'll have an arbitrary element from here, so that will just be A composed with, and we'll have to make it little h prime, because we don't want it to be the case that these two have to be the same, okay? So little h and little h prime are just two elements from the subgroup, okay? So if it were the case that there was an element in this left coset of H under B that was equal to an element in the left coset of H under A, then this would be true for some little h and some little h prime are elements of the capital H. Okay? Right, so this would be true if it was the case that these two had a non-empty intersection. Okay, but then quite simply what you can then do is compose on the right with little h's inverse. Now when you compose on the left hand side here, on the right on the left hand side of this equation with little h inverse, what will happen? You'll get little h composed with little h inverse here. Now of course that is just the identity element, so this just becomes little b. On the other side of the equation, what you'll end up with is little a composed with little h prime composed with little h inverse, like so. Okay, now why is that very interesting? Okay, well the reason that is very interesting is if we consider this, we've got little h prime here composed with little h inverse. Now little h was assumed to be an element of the subgroup, so that means that little h inverse will also be an element of the subgroup, and when we compose two elements of the subgroup together, as indeed we're doing here, we're composing little h prime with little h inverse, we will end up with some other element of the subgroup, so we could call this little h bar. Okay, so now what I have done is I have written B as being equal to little a composed with little h bar, where little h bar is some element of the subgroup capital H, i.e. I have just managed to prove that little b is an element of the left coset of capital H under A. Okay, so b is an element of AH, like so. Okay, so I've proven to you then that if it were the case that there was some element in this left coset of H under B that was equal to an element in the left coset of H under A, then I can prove that little b was actually an element of the left coset of H under A. So if it was the case that you had picked a little b that was outside of both the subgroup and the left coset of H under A, then its entire left coset has to be outside of those as well. Okay, right. Now you can continue this process on. Okay, now what you can do is, okay, either these three here, the subgroup along with these two left cosets of the subgroup, either they make up the entire group and there's nothing left outside of them, okay, or there is another element outside of them, call it a little c, and what you can then do is generate the left coset of capital H under C. And I'll just colour this one in as well. We'll have this one now in green here. Okay, and this too has to be completely distinct now from all three of the prior things. It has to be completely distinct from the subgroup capital H, it has to be completely distinct from the left coset of capital H under A, and it has to be completely distinct from the left coset of H under B. Okay, now of course we know that it will be distinct from the subgroup, but we can now apply this exact same argument for why it's going to be distinct from the left coset of H under A, and then why it's going to be distinct from the left coset of H under B. We can apply this exact same argument, and we can prove that if that were not the case, then we can prove that little c will be in one of these, basically. Okay, so if it's the case that you can find a little c that's outside of all of the cosets that you've generated so far, then its entire left coset must also be left over, basically. So you can't ever just have C on its own. There must be all of the elements within its left coset of H also there, basically. Okay, right, so you can continue this process on until finally you have completely covered the entire group. So in my picture it looks as though we've got one final coset here, so let's say we've still got one element, little d, that is absolutely outside of here, and of course little d can't be on its own, it must have its entire coset also out here, okay, and I'll colour little d's coset in turquoise here, and you can continue on thereby partitioning the set, and all of these cosets that you're generating will be completely distinct from one another, and together they will cover the set, because you can just continue on until the point that you do have a collection of cosets that cover the set. If you've got ever an element that's outside of all of the cosets that you've produced so far, you can quite simply generate its left coset, and then you've got another one to add into your collection, and you just keep on going until you have finished, basically, and covered the entire set. Okay, so that then is how cosets can be used to partition up the set that underlies the group, basically. Okay, and you can do the exact same thing for right cosets. The exact same thing holds true for right cosets. And if the subgroup that we were using to generate these cosets was a normal subgroup, then it will be the case that the left cosets and the right cosets will be exactly the same. So this partition will be exactly the same. Okay, the other thing to note is that it really does not matter which little a, little b, little c, and little d you use. Okay, remember the fact that all the elements of these cosets generate the exact same coset. So these are just representatives of these cosets, but you could have picked loads of different elements and you'd have got the exact same partition. So I want to stress, this partition was not dependent on the way you chose these arbitrary elements here. You could have chosen whichever elements you like from the remaining portions, basically, and you'd have got the exact same partition. So it is unique, basically. Okay, so if you decide to partition up your group with the, let's say, left cosets of a subgroup capital H, there is only one way to do that. Do not get confused and think that there are different ways of doing it depending on which little a, b, and c, and d you pick. Okay, that's not the case, because remember we proved that fact that the all the different elements within a coset will always generate that same coset back again. So there is one way to partition it up with the left cosets, basically. Okay, right. So that then is now going to lead us on to Lagrange's theorem. Now Lagrange's theorem comes when we apply this idea to finite groups, okay? So it doesn't apply for infinite groups, it's only in the case of finite groups. Okay, so we are now assuming that the order of this group, capital G, is finite. Okay, so Lagrange's theorem then. Okay, right. So basically, Lagrange's theorem says that the order, i.e. the number of elements in the large group, okay, written like so, modulus of capital G, and read the order of capital G, which just means how many elements you have, how many symbols you have in the entire group, basically, okay? It has to be some multiple, which I'll call little n, okay, where little n is going to be some natural number, okay, of the order of your subgroup, basically, okay? And this is often stated in a different way. This is often stated that the order of any subgroup of a group must divide the order of the larger group. So this line here means divides, okay? So it means exactly this, that some multiple of the order of the subgroup must equal the order of the group, okay? So, when you look at the order of the subgroup here, you have to be able to times that by some natural number, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. All the natural numbers, the counting numbers. There must be some natural number that you can times that by to get the order of the group. Or rather, you cannot possibly have a subgroup of a larger group, capital G, that does not have an order which divides the order of the group. So let me give you a concrete example of this. Let's say we have some group which has order 10, okay? So its order is 10, it has 10 elements within it, okay? Lagrange's theorem instantly tells us that you cannot possibly have a subgroup of order 3. Okay, there cannot possibly exist a subgroup of this group of order 10 of order 3, because 3 quite simply does not divide 10. Okay, no natural number times 3 gives you 10. On the other hand, you could have subgroups of order, for instance, 5, because 5 does divide 10. 2 times 5 would equal 10. Or you could have a subgroup of order 2, or indeed you could have a subgroup of order 10, or 1, those are the two trivial subgroups, the entire group and just the identity subgroup. Okay, so this is a very powerful theorem. This tells us instantly what orders subgroups can actually have, basically. Okay, so it curtails hugely the number of subgroups that are plausible, basically. It tells you that you can never have a subgroup which doesn't have an order which divides the order of the group. Now, why does that come very naturally from what we have done? Okay, well, it's because we have just shown that we can use these left or right cosets of a subgroup, capital H, to partition up the set. Now, the left or right cosets of this subgroup, capital H, if we're talking about finite group theory, the left and right cosets are going to have the same number of elements in them as the original subgroup. Okay, so we're now assuming that the order of the subgroup is finite, so it's some number. Okay, let's call that number little m. Okay, where it will be some natural number, 1, 2, 3, a counting number, the number of elements that are in capital H. Okay, all of these cosets must have exactly the same number of elements in, okay, because we know that the cosets, the definition of the cosets, is that they are just all left or right multiples of the elements of the subgroup by a certain element, basically, okay, and we know that all the answers that you get are distinct. So basically, what we can say is that the order of the left coset of H under A will always be the same as the order of the subgroup. Okay, and that is also true for right cosets of H under an element A. Okay, so that means that all of these cosets will have exactly the same order as the order of the group. And now what we're saying is we can partition the group up into lots of these sets of this same size, which means that the size of the entire group, capital G, must equal some natural number times capital H, where this natural number here is just the number of cosets you actually have in this group, capital G, basically. So how many cosets you partition it up into, that's your number, little n here. So it comes very, very naturally from our understanding that we can partition a group up into the cosets of a subgroup, basically. Okay, so, as I say, this concept of partitioning it up, this applies to infinite groups as well. You can't quite use this sort of finite logic here in the case of infinite groups. Okay, so Lagrange's theorem is a theorem that relates to finite groups, and it says that you cannot possibly have a subgroup of a group that does not have order which divides the order of the entire group, and that is a hugely useful theorem for deciding instantly whether or not a subset of a group can possibly be a subgroup. Okay, if it has an order that does not divide the order of the group, you can instantly say, no, it can't possibly be a subgroup, and that's a very powerful thing to be able to do. Okay, so we'll continue this discussion in the next video where we'll see a huge use for Lagrange's theorem.